Good afternoon, everyone. Welcome to our second day of Lincoln Math and Physics Week. My name is Professor Andrzej Zwilendowski. I'm head of School of Mathematics and Physics. And before we start our lecture, I give a few words of introduction. To the event tonight. And the first few minutes will be the same for every hour during this week, simply because then people come to a particular hour, they might not listen to the previous one. However, if you've been already to one of the previous lectures, yes, few first minutes will be the same. So our standard lectures are usually live. Then people come to the campus and they can enjoy a view of a beautiful waterfront campus in Lincoln. However, in these times, we have to do everything virtually as basically due to pandemic, and we try basically the best we can in these times. Lincoln is not only beautiful campus, it's very lovely city of approximately 100,000 inhabitants. And if you walk through the campus just 10 minutes, you end up in the center of the city, which is quite old. It was founded by Romans in the 1st century AD, soon after they came to the British Isles. It was a home of famous 9th Legion, Hispania, prior to the Legion moving to York. It received the prestigious status of Lindum Colonia already in times of Emperor Domitian. And you still can enjoy some of Roman remains, like walk under the Roman arch in the center of city. Next big step in development of city comes almost 1,000 years later, in the time of next newcomers, William the Conqueror, William I, who ordered to build the famous castle of Lincoln and even more famous cathedral, Lincoln Cathedral, which is probably one of the most beautiful buildings, not only in United Kingdom, but in the world. And in fact, for about 200 years, it was the tallest building on the planet. Then its spire, wooden spire, was still there. Lincoln Cathedral, of course, was a seat of learning, but the university in Lincoln was founded only at the end of 20th century. In 1996, the first beautiful building in the campus on Brayford Pool was opened by Her Majesty the Queen. And already in 21st century, College of Sciences appeared, including a School of Mathematics and Physics, which opened its doors in 2014. And 3 years later, I've got own building, which next month will celebrate its 4th year. Isaac Newton building shared between School of Mathematics, Physics, Engineering, and Computer Science. And as our school hosts lectures which aimed at those who study math and physics at A levels, but not only. I'll mention what we have to offer to those who might consider studying mathematics or physics further after A levels. And that includes all range of degrees from bachelor to integrated master degrees in physics or mathematics, as well as join with another ancient science discipline, philosophy, both physics with philosophy and math with philosophy, and joined also with computer science and between mathematics and physics. And tonight we have lectures which also celebrate International Women's Day and the contribution of female scientists in the mathematics and in physics. And I am very happy today to welcome our speaker, Dr. Manuela Mura.
Hello, Amir.
Hello, Manuela.
Hello.
Welcome here to our special day. And I just say a few words about our speaker this afternoon, Dr. Manuela Mura. She is originally from Italy, specifically from Sardinia, where she obtained her undergraduate degree in physics in and then she moved to United Kingdom for her doctorate study in King's College London, where she obtained PhD in 2010 on theoretical characterization of scanning and tunneling microscope images of assembling of flat organic molecules on metal surfaces. That, of course, very, very long title, but what is inside is a lot of computational theoretical physics work on Nano-Physics, which is also subject of today's talk. For her PhD thesis, Manuela received 2 awards. One is a quite distinguished Tedion Riedel Prize for Molecular Science from King's College London, and another is Springer, a publisher Springer PhD Thesis Prize, also in 2010. Manuela worked as a researcher after her PhD at University of Central Lancashire in Preston, and in 2014, she was part of the founding team of our School of Mathematics and Physics here in Lincoln, where she is now a senior lecturer. I'm very happy to give a floor to Manuela tonight for her talk on how nanophysics contributes to nanomedicine. Let's enjoy.
Hello, I'm Manuela Mura, and today I'm going to talk about nanophysics for nanomedicine. The main topic of these talks are antibacterial peptides. So I will talk about what they are, how they interact with bacterial membranes, and I will discuss about the methods they use to analyze the result and some general knowledge as general results that have been published previously. Nanophysics is the part of physics that is halfway between quantum phenomena and macroscopic phenomena. From one side we got quantum law, and the other side we got Newton law. And this allowed us, this part of physics allowed us to describe structural, electronic, optical, electrical, and also thermal properties that can enhance our knowledge in nanomaterials and improve even further the nanotechnology. On the other hand, nanomedicine is the branch of medicine that use nanotechnology and nanomaterials to cure disease and various illness. Two main parts at nanomedicine is focused on drug delivery and antimicrobial agent. The reason why I'm interested in antimicrobial peptides is quite known, because as you in the last few years the resistance of bacterial to some antimicrobial agents and antibiotics increase quite a lot, and that will bring to the development of superbugs that will decrease the lifespan of human and no humankind in a short time. This slide shows essentially the percentage of different isolate resistant to different drugs, and in the right side we got the percentage reported cases that are resistant to antibiotic for different kind of bacterial and in function of the time as well, the year. And as you can see, there is still quite an increasing. What are antibiotic peptides? Why they look so interesting from the pharmaceutical point of view? Essentially, they are part of the innate immunity system of living organism. They are themselves living organisms, usually are small proteins that have a wide spectrum activity and then can be very effective against bacterial, fungi, virus, and other kind of disease, and can be also very, very efficient against different kinds of cancer. For example, I use one of the peptides that I use in my simulations where are M5, that is a peptide that is present in the skin of toads. The toads are quite aggressive kind of animal, they fight quite a lot, and the presence of peptide somehow improve the ability to heal the wounds and avoid the infections and preserve the life of the toad, the toad, essentially avoid that they get weak. So let's see a little bit about how do they look, these antimicrobial peptides. So the one that I use, they are this kind of antibiotic. So we use Aurine 2.5, Aurine 2.6, that are the same kind of family. Modeling 5, Aurine 3.1, that again is in the same family of aurines. As you can see, they are composed by, they are small protein, they have 12, 16 amino acid, and another characteristic of this antimicrobial, they are helical. So these different color balls and sticks are essentially the molecules, and the helix that you can see is a secondary structure of the peptide that is formed, depends what kind of hydrogen bond are formed between the amino acid on the protein itself. Another possible secondary structure that they can have is the beta sheet, that where essentially the hydrogen bond are formed between amino acids in such a way that we have a strand. And this secondary structure we will later, it's quite important when we go to analyze the insertion as well. The other part that I'm interested in is the lipid bilayer. The lipid bilayer essentially is one of the components of the cell membrane of the bacteria. As you know, the bacterial is essentially formed by a cell that is composed by the internal organs in some way that are complete, and then there is a wall formed by these lipid bilayer proteins and different objects that are important for transfer information or exchange information from inside outside the cell, and they are quite important for the life of the cell itself, so the bacterial cell in this case. And these lipid layers are formed some kind of very, very important element because in some way create a protection for the lipid for the cell and to differentiate quite the internal part from the external part. And the way how this lipid layer assemble in such a way that is like a double layer. So if we focus a little bit on the composition of the lipid layer, we can see that this is this long molecule that is mostly a fat molecule composed by this hydrophilic bit that can easily link with the water, and the hydrophobic part that is doesn't like to be in a water environment, and then they stick together and create a very dense and strong structure. And then the hydrophilic part and the hydrophobic part are linked using this phosphate group that is the brown bit, and then differentiate what is called the head group from the tail group. Once we do have we are in water environment and we have a lot of them, they assemble in such a way that we got a double layer of these molecules, where we got here the hydrophilic bit, that is, for example, if this is the internal part of the cell, this is the external part of the cell, the hydrophilic bit face the water, while the hydrophobic part stick together, forming again this dense part. But everything is quite flexible, and this lipid bilayer move quite fast. The other thing that I'm interested in how they work. So how they the peptide interact with the membrane, and then essentially I want to see how they interact, how they disrupt the bacterial membrane, and finally kill the bacteria. So the mechanism, that there are several mechanisms that have been observed, and all these mechanisms depends very much on the physical chemical properties of the environment. And essentially we can see there are several methods, but all of them aims to essentially kill the bacterial cell, and make the host free from the disease. The method that I use is called molecular dynamics. The molecular dynamics consider each part of the system composed by atoms, so the basic unit atoms, and we can simulate nanoscale phenomena. This again allowed us to describe the structural functional properties of the lipid bilayer and the peptide, and see how they interact with each other. And the molecular dynamics can easily run knowing only and mostly all the essentially the Newton law. In particular, what we do, we solve the Newton law, and then we find how the position of atoms, how the position of molecules change in function of time. Of course, the potential here, that is this gradient of V, is not so simple. It's an empirical potential that has essentially two main bits. One is this sigma bond, single angle, sigma torsion, that are characteristic of the short radius interaction, essentially characterize the chemistry of the system, describing the covalent bonds and how the atoms are linked together. And the second bit, that is called non-bonded or long interaction part, where essentially are included all the physical properties of the system, where the atoms are essentially considered charged, and the van der Waals rule, again, equation, the van der Waals interaction as well. But that is enough, considering that all these parameters K and V and sigma and are essentially empirical values that are input beforehand on the simulation part. And then once we know all those elements, we can start to characterize our system. The first characterization is characterization of lipid layer. So in order to be sure that my system works, what I have to do is somehow compared with experimental values. So everything will be compared with experiment. And then, as I said, what happened is I put in my system simulation the lipid layers. I tune the condition, a physical condition, and after a while I will see outside this double layer of a membrane. And in order to be sure that what I'm observing is something that is real, I have several tools. One is the area per lipid, that is something that it can be measured experimentally. Another one is this density profile that can be compared with neutral scattering profiles and tells me how essentially it gives me information of electronic density of the lipid layer and density as well. And to understand a little bit how does work this plot, we need to see that essentially the continuous line essentially is the density of my lipid layer, so it's overall where tell me where I can find the lipid layer, while the dot line tells me essentially the density of my head groups that, as you can see, are aligned exactly on the boundaries of the lipid layer. And this dashed line is the density of the tail groups, that is the center of my wall. Again, we have this brown density that is essentially the density of the phosphate group. Once we know sure that the lipid layer is okay, what we can do is just start to analyze how the profile change in presence of the peptide or the drug. In this case, it's the BDP. BDP, that is a anti-asthma drug in presence of the MPC. The MPC is the lipid layer in a water environment. This simulation shows how essentially starting from one configuration of 4 Armstrong distance of the peptide or the drug respect the walls of the lipid layer, after only a short period of time the drugs goes on the interface, and then I can analyze how the density profile change when the peptide or the drugs is on the interface, and also how the area per lipid change itself. And that is quite important because show me how essentially the quantity, how much the lipid layer will be disrupted by the prevalence of the peptide. Again, I show you some profile changing of profile with different configuration, and again that is quite evident either in shape changing, either in essentially unit quantities. Now a very important part that I said for the peptide lipid layer interaction is the secondary structures. From some experimental results, it appears that the peptides are more effective interacting with lipid layer, therefore inserting the lipid layer if they have a alpha helix configuration. So I run simulations of the peptide in water, and also in presence of lipid bilayer with different orientation of starting of orientation of the peptide respect the lipid envelope. As you can see from the simulation, we observed that in water there is quite a lot of disruption of the secondary structure. So there is not alpha helix, but there is quite of changing on the structure, and then looks like the peptide it's prefer to be in a beta sheet configuration rather than in alpha helix. So the red it's essentially a beta sheet. The yellow is the turn, so it does show how the central part of the peptide change, and then the green one is a band. So again, how does it change in function of time? Because that between 0 and 200 are essentially nanoseconds. The other two configurations show that one part of the peptide is preserved is secondary structure, alpha helix secondary structure. And this is a good relation, in this correlation with some experimental result obtained using circular dichroism. So the gray line here is the peptide in water environment, and then again this shows that there is no structure, and that is essentially what our result agrees with what is observed experimentally. And the second part, that's the black line, shows that the presence of this band here, or this peak or minimum around 200 nanoseconds, is a typical configuration of alpha helix. So the experimental result show that there is if there is a lipid bilayer present in the environment, the orange prefer to be on helical configuration, and that is again is in good agreement what we found out. Another interesting part, that once we know that the helix is important, the other important thing is check what amino acids are involved in the interaction with the lipid bilayer. And here essentially we observed that there is some leucine 6 and 7, valine and leucine again are important for the interaction with the lipid bilayer, and are quite and then kind of make more favorable the insertion of the peptide into the lipid bilayer. But on the other hand, in this kind of configuration, we have the lipid bilayer in one side and the water on the other side. So when we some amino acid will be interacting with the water on the other side, and when the pore is formed, some way they insert in a region that is hydrophobic some water. The presence of water will imply that there is some kind of pore formation that destabilize the presence of destabilize the lipid bilayer, and then can lead to the disruption of the bacterial membrane. And that is essentially what I was trying to explain. So we do have the fact that some amino acids, that are this blue one here, interact strongly with water, and they are trying to make a favorable channel for the insertion of the water. In this picture, the lipid bilayer is the white region, because the brown are essentially phosphate of the lipid bilayer. So they can this shows how essentially the lipid bilayer is disrupted from the presence of the peptides inserted. Again, quite a lot of information can be consider checking the profile density and showing how the lipid bilayer and the system are changing. Again, this tells me as well how much the peptide insert in the lipid bilayer. Finally, one other configuration that we were considering was this, before I talk about Q orientation, H orientation, our favorable to have a helix configuration rather than a random coil. And this essentially shows how the peptide insert in the lipid bilayer, and then how favorable was the insertion. Another final use of the molecular dynamics is to consider essentially the profile of energy. So the fact that the bacterial has this interface to this double layer of that is the whole consisted mainly by lipids, and these lipids have this hydrophilic bit that can link easily with the water, create from a physical point of view energy barrier that can be more or less favorable to the insertion of a molecule. So this study we did an analysis considering pulling essentially the molecule on the lipid bilayer and calculating point by point the energy on that at that point, evaluating this plot of energy to see what if was favorable or not inserting them in a particular environment. In this particular case, we just considered two different environments. There was BDP plus lipid plus water, and in the second case, we include ethanol. Now, as you can see, doing the same exact, starting from the same point and relaxing, inserting the lipid bilayer, we observed that the system in presence of ethanol, that was 2.5 ethanol water percentage volume, we did can observe the decrease of the barrier of 1/2 compared to the system where is present only water. And that was quite important because this work was related to some experimental values that for liposome. So they synthesize liposome in presence of ethanol, and then the presence of ethanol that was always favored the insertion of the drugs. That was a good result because this kind of drug was designed to drug delivery and to be inserted essentially inserted in the walls of the liposome, carried on the target position. And so that was quite interesting result. Finally, I just show you some simulation of random values of random peptide that start from essentially a random configuration, and then at some point they deposit on the interface of the lipid bilayer. So I hope to show you how important can be molecular dynamics to investigate the interaction of antimicrobial peptide and the lipid bilayer. We can tune the bilayer and the antimicrobial peptide as we wish, and we can essentially increase the effect. We can also change, mutate the antimicrobial peptide, change and trying to investigate different possible drugs. Again, always considering and checking with experimental results. So thank you for listening. You can find us in different ways. These are the link, and I'm happy to answer your question. Thank you.
Thank you very much, Manuela, for your talk.
Thank you. Let's be okay.
And now we have time for questions. So I just remind there are 2 channels to ask questions. You can type in your questions directly in live chat in YouTube. And we will try to read there, and also in a Padlet, if you'd like to do it anonymously. There is link to the Padlet either in your emails or in a live chat on YouTube. You can see the link, and then you basically can ask questions both ways. While during talk, some questions in fact arrived to Padlet, but you can type your questions in either of those channels. And I think Manuela can see the questions, but I'll just read them because people won't see the Padlet. If you click on the Padlet link, everyone can see these questions as well. So, and again, there are no no wrong questions. So please ask whatever you like to ask. So I see there is question here says are the lipid bilayers the same for different animals like toads and humans? Probably because you showed different snakes and toads, and so maybe you can say some words on that.
So the lipid bilayer essentially are part of the cell. So it's the main differences between eukaryotes that are essentially animals and the bacterial or protozoos. So yes, they are very similar in composition, but they can essentially the head group can change according with the environment. But the main component of the lipid bilayer are very similar. Yes, the cell of course is complicated, but.
Thank you. Now I see a question, another one in the Padlet as well. It basically says, what physics laws do peptides follow? It's probably quite a complicated question.
Yes, it's quite complicated. What I impose in that case is that is verify Newton's law. But we do have also some parameters in my computer simulation that include the thermodynamic properties and several other checks that essentially try to respect, let's say, the general condition of perfect gas in some way. So the particle, as I said, each atom of the peptide is a point atom, and they are connected using a covalent bond. And then we do investigate the interaction between the peptide and the other component using van der Waals and Coulomb interaction. So essentially, it's classic laws of the physics in some way adapted to this kind of system, and work, let's say, quite well. Again, according with comparing the result with the experiments. I don't know if that's okay.
Thank you. And there are more questions.
I did.
It says, how long does it take to run your simulations?
It depends on the system. At the moment, I'm doing some simulations that are composed by a molecule, one single peptide, and 256 lipid bilayer and 10,000 water molecules, and I can run in my own machine. Okay, it's in my computer in about 1 week, 200 nanoseconds. So it depends what kind of result you want to do. The system is small, but you can get the result now at the moment in about 2 weeks. And then analyze the result is a little more complicated. Okay. Is okay.
And then there is a question, is this mechanism that antibodies use to disrupt bacteria?
That is okay. This is a particular property of these antimicrobial peptides. So this it's yes, and they kind of it's been observed experimentally with different different experiment in vivo and in vitro that they act in this way. With the slide that I showed, where essentially there were the different mechanism. Depends on the bacteria, the composition, no, the bacteria, so depends on the peptide, the composition of the peptide, you can have different ways, but the main idea is to kill the bacterial membrane or the cancer membrane or the or any other kind of pathogen membrane, yes. So they get rid of these bad cells, and our body in theory is stronger.
I see there is a comment on the answer in YouTube from Chris about 200 nanoseconds in a week. So can you maybe comment on that? Can it be done fast?
Okay, it's my computer machine in the office. Can be done faster with a supercomputer, but 200 nanoseconds is not long, because 10 years ago when I started, I could do 1 nanosecond in 1 month. So it's a good improvement, I can tell you, yes.
And then it basically maybe it connects to next question I see in the Padlet. Can we create new medicine on computer?
Well, okay, so in principle, it's already what happened, no? They have some kind of libraries, and they select, they know that these drugs works in some ways differently, and then they select the library that they want, the medicine that they want, and then they can modify it to in such a way that they create, that can be more active against some pathogens. And Andre will be very happy to that, but it's essentially the way out. Vaccine, they create the vaccine, right? In some way, in very similar way. But yes, in principle, yes, can be created by computer, of course, with different. It's not only a physicist that can help, but mostly we need chemistry. We need the chemist, life science, biologists. We need to know quite a lot about how the antimicrobial or how the drug works to be sure that it works in the way that we wish. But yes, in principle, yes, we can use a computer to do the new medicine.
And then I see there are more questions. What program do you use for your molecular dynamics simulation? And is this something you can run on your local machine? You partially answered, but just maybe a bit about, is it something very special computer program you use for this work?
Yes, it's a molecular dynamics program called GROMACS, but there are several other programs around that can run simulation like that. One is Amber, the other one quite popular at the moment is NAM-MD, and all they are more or less on the same principle after Calpus essentially develop the biological methodology to describe these kind of biological systems, yes.
And is it the same Karplus who got Nobel Prize?
Yeah, the same Karplus who got the Nobel Prize for, yes.
Right. And okay, there another question I see, Padlet. How did you decide to study this topic?
It's a little personal, this, but it's because it's quite a challenging topic. It's as Andre said before, the system, usually these peptides work in a very complicated ways, and it's often very, very difficult to get a solution because we apply some mathematical methods to understand how does it work. We expect some kind of result, while it's always something that is challenging and new in some way. So I always be interested in understand how life develop, right? And physics in reality can explain partially the life. And with this topic, I'm trying to essentially put together something that use the physics to explain how kind of life develop in some ways, right?
Thank you.
But essentially was thanks to some experimental people that was working on the topics on the and then because I was interested in the topic, I just decided to help them in some way.
And then there is an interesting question, which is, I think, relevant to general of this nanomedical research. How do you ensure that peptides will not affect non-pathogen cells in the body while attacking the pathogens?
Okay, that is another big problem. So once it's somehow related to when I said that we have check the libraries, right? So we select some particular drugs, and the steps to get in reality to work are several. So we check the drug. We see what kind of bacterial are. As I said, they are different bacterial human cells. So if we're talking about pathogens, for example, so we just target this kind of systems. And also after I do check how they interact, there will be several steps before we use the drug. So all the biophysical and biological component essentially checks that they have to go through to be essentially on your pharmacy are quite long procedures. So I just on the beginning, and then everything else come after me. I hope that makes sense, but
yeah. So basically, you've been in fact answering which question just arrived in Padlet, which tells, do you think peptides will be once replacing standard antibiotics, and how quickly the new drugs will be available? So it is still beginning of the path.
Yes, still developing, yes.
And then there are questions there was some general question there about your inspiration figure. Wait a second, where it is?
I didn't see
Who is your inspiration in science?
Oh God. It's a difficult question. I usually go. I can't tell you big names, but they usually go close me. I start my inspiration start when I was in at university, when I see how hard some of my supervisors was working to do to achieve what he does, and how much was trying to get the enthusiasm that he was putting on running simulation or understanding, for example, particular systems, and that is quite inspiring from my point of view. I mean, there are a lot of figures that are kind of difficult to achieve, because I cannot say that I can compare myself with Einstein or someone else. I'm just a little more looking people that manage to be successful in their little, in their, let's say, in the little space. But it's very nice to see your simulation, for example, complete to achieve what you want in terms of creating some kind of system and seeing how this peptide interact with them, for example. But I don't know. I think I'm going for local people rather than big people. But of course, it's if I think a little bit, probably I can find someone important that I like. But I go in first to my first supervisor and second supervisor and people that work on the field every day, even achieving Nobel Prize.
Okay, thank you very much, Manuela. And I think your work, what you do, can also serve now as inspiration for other people, in fact. And I'd like to thank you again for giving this talk. And I just, in case somebody came a bit late, to emphasize, we try to basically celebrate today on 8th of March during International Women's Day the contribution of female scientists to science. And some of you might know that Lincoln is the birthplace of once very famous mathematician, Charlotte Scott, who was not allowed to have a formal graduation in Cambridge in her time as a female student. Still, she succeeded and became a very famous person. And now we celebrate today contribution of contemporary physicists and mathematicians and sciences into science, also here in Lincoln, and Manuela is one of them, and I'm very fortunate to work together with Manuela. Thank you very much for your talk today. Thank you.
Thank you. Thank you for listening. Bye. See you later.
And bye-bye. I wish you all goodbye. And if you join us for another event, one in a few minutes or another day, I will be very happy to see you all. Bye.